Math 1314, Tyler Junior College, section 2.5, transformations of functions, reflections across the x and y axis. So far, we've looked at 8 common functions graphs, and we've discovered transformations to the actual function that invoke translations on the graph of the function, moving the graph up, down, left, or right, without flipping it or, excuse me, or stretching it in any particular direction. We're now going to explore what transformations you perform to the function to invoke a reflection on the graph. In other words, we're going to either reflect it and take its mirror image across the x-axis, or reflect it and take its mirror image across the y-axis. I'll tell you right now that the thing that invokes these reflections are the presence of negative signs, equivalently multiplying somewhere by -1. And if you notice, these two functions are pretty much the same, with the exception of where the negative is. Graph f of x equals negative square root of x. Graph f of x equals the square root of negative x. Now before you look at the second one and say you can't square root a negative, well, first off you can, but we're not, because we're avoiding non-real numbers. And secondly, this can be real if the x is negative, because if the x is negative, then the negative x of x will be positive. But both of these are based off of the graph of the square root of x, which is the top half of a parabola opening towards the right. So let's see if we can figure out what's going on here. If we were to create a table for f of x equals negative square root of x, it would be the same as the table for this. For example, 1, 1 is a reference point on this graph, so is 4, 2, since the square root of 4 is 2. But this function says square root your number and then stick a negative on it. So if we took x equals 1 and square rooted it, we would get 1. But then if we took a negative, put a negative on it, it would reflect it down here. So here's where 1 would end up being if I stuck a negative on it before I plotted it. And the same thing for 4, 2. If I just square rooted it, the square root of 4 is 2. But this function says, now stick a negative on it. Okay. So 4, -2 would be down here. And by the way, 0, 0 is a pretty important reference point for this graph as well, since it's where the graph starts. Sticking a negative on a 0 won't change it. So if I reconnect them, knowing what shape I'm looking for, what happened to the graph of f of x equals the square root of x to give the graph of f of x equals negative square root of x? Answer, the graph was reflected across the x-axis. My symbol for reflection is kind of some little loopy arrows here. Kind of like this graph is coming out into 3 dimensions and rotating that way. So it seems like putting a negative in front of the function will invoke a reflection across the x-axis, and you would be correct. I'm not going to write the entire sentence. I will say it. If g of x equals negative, well, I'll write it down. If g of x equals negative f of x, comma, then the graph of g of x is obtained by reflecting the graph of f of x across the x-axis. Or in short, if you stick a negative in front of a function, you reflect across the x-axis. So what do you think will happen on the other one? Well, by process of elimination, it's probably going to reflect it across the y-axis. And we would be correct, but let's think about y for a second. My reference points over here, only 0, 0 is good. I can't put in 1, I can't put in 4. What's wrong with finding f of 1 here? If I put 1 into the function, I'm square rooting -1. That's not real. We want to stay away from that. However, I substituted -1 into the function, then this negative would turn it positive and the square root of it would be 1. So I can put in -1, and when I do, I'll get out +1. I should mention that the point at the origin will stay there because -0 is just 0 and its square root is still 0. And let's think about the point 4, 2. I can't put 4 into this function because that would ask me to square root -4, which is 2i, but we're not plotting non-real numbers on this coordinate plane. However, if I substituted -4 here, then the other negative would turn it positive, square root would come out to be 2. So I can substitute -4, and when I do, I'll get out +2. And now that I have some points to refer to, -4, 2, I can resketch the graph, and now it looks like we indeed did invoke a reflection across the y-axis. In other words, we took this graph, reflected it over here, and we got that one. So the whole sentence would say if g of x equals f of -x, meaning I put a negative directly on the x, not in front of the whole function, then the graph of g of x is obtained by reflecting the graph of f of x across the y-axis. Or in short, f of -x, meaning that you put a negative directly on the x, reflect across the y-axis. The reason I picked the square root function is because some of these graphs, it's tricky to tell which way you reflected it. For example, if I took the negative and stuck it inside the absolute value, took that v and reflected it across the y-axis, it would be the exact same graph. I couldn't tell that a reflection occurred. Or if I took the x cubed and reflected it across the x-axis, it would be exactly the same as if I reflected it across the y-axis. If you're an odd function, reflecting across the x-axis is the same as reflecting across the y-axis. Yes. For example, if I took the 1 over x, reflected it across the x-axis, the branches would land in quadrants 2 and 4. But if I reflected it across the y-axis, the branches would still land in quadrants 2 and 4. So if you have an odd function, reflecting across the x-axis is the same as reflecting across the y-axis. I challenge you to review the definition of an odd function and confirm it algebraically, what we just said, that for an odd function, these two things are equal. It's not actually that hard to prove. So that's a reflection. Stick a negative on the x, reflect across the y-axis, stick a negative in front of the function, reflect across the x-axis.